they're trying to get you to distinguish between the different types of definitions: rings, integral domains, and fields. Rings, it's nice to think of this in terms of a visual. Rings represents the big picture, so it's the black set. And integral domains are shy of being rings because they don't have multiplicative inverses. Fields are the most restrictive and the smallest of the three sets. So when we start looking at these problems, many of the problems that they ask in number 33 have something to do with looking at it in this kind of way, which is more restrictive. So the first question, every field is also a ring. That's true because you see that fields are the innermost sets. Fields are rings with additional properties. So they're more restrictive. Part B asks whether every ring has a multiplicative identity. That's not true. And of course I'm lazy, so I'm going to make the simplest possible example. The 0 only, with plus and times defined as 0 times 0 is 0 and plus is 0 plus 0 is 0, is the trivial ring is definitely a ring, and it has no multiplicative identity. Every ring with unity has at least 2 units. Well, that's false. If we look at R equals Z2, that's certainly it's not only a ring with unity, it's a field, but it only has 1 unit, 1. Every ring with unity has at most 2 units. Well, what they're saying is that R has that something is maximized by 2 units. That's not true either, because R has an infinite number of units, and R is definitely a ring with unity. R is a field, in fact. E, it is possible for a subset of some field to be a ring, but not a subfield. That's true. If we take R equals the ring equals R, that's definitely a field. But if we take this trivial ring inside R, it's a ring, but it's not a subfield because there's no multiplicative multiplicative identity. And this is more of Fraley being funny. The distributed property is not important. We've used it a couple times in proofs. I didn't know whether to say true or false, so I just say what? And then finally, we have some questions about fields. Multiplication in a field is commutative. This is true. This is a property of fields specifically. H states that the non-zero elements of a field form a group under multiplication. That's the definition that I gave you, so this is definitely true. And addition in every ring is commutative. Absolutely true, because that's the way I defined it for you, that R with plus forms an abelian group. Every element in a ring has an additive inverse. That again is true because R plus with the plus as the binary operation is a group. Again, I told you when we started that the definitions that I provided with you, laying out the structure in terms of the groups is the appropriate way to think about things. And I in fact talked about Hungerford and my disapproval of starting out with rings and fields first. This is why I have that disapproval, because you're really starting with groups and building more structure on those groups.